All right, before we start with the actual lecture, one more introduction. This is Lucy, one of our tutors. She's the one who HD'd AOS after 1 year after she wrote her first program. So she's awesome. Like all our tutors, actually. All right. Well, so yesterday, day before, I gave you a very quick introduction in microkernels in general and seL4 in particular, and then started to dive into the seL4 mechanisms and concepts. And I covered the protected procedure call. What's happening here? Okay, might be the projector.
Yeah, the stream has the correct slide off.
It's still okay? Yeah, okay, cool. So specifically, I covered the IPC mechanisms, which, as I said, you should think of as a protected procedure call, executing a function in a different protection and addressing context, and notifications, which are the basic synchronization mechanisms. And today I go through the remaining mechanisms, so caps, memory management, threads, and interrupts and exceptions, and talk a little bit about sort of general approaches to system design. Only a couple slides, which should hopefully be helpful for your project, and then you should be good to go. Any questions until we go into that? Any leftover questions from yesterday? No? All right. Then and this thing is not working. It was before. All right. Then mechanisms, capabilities. So we already, I gave you an introduction what capabilities are and gave you an idea of, well, basically explain that they are kernel objects, so the user doesn't have direct access to them. They do live in the kernel. And there's a number of operations you can do on capabilities. The core operation, which is what they're there for, of course, is to authorize system calls. So any system call in seL4 is, with one exception, unfortunately, is invoking a capability. But that's not the only thing. This is what you usually use capabilities for, but it's not the only thing. The other thing is operations on capabilities themselves, and this is the capability derivation operations. We've seen one of them, badging. I introduced badging as a way of stamping a capability so you can recognize it again. And that's used by servers to distinguish between different clients and associate client state with clients. But there's more than those. There is the, well, mint operation is what does the badging. So, but it can do other things as well. In general, mint creates a new capability that's derived from the previous capability with generally lesser rights. So one version of that is batching. A batch capability is more restricted than a general purpose capability because for one thing you can't batch it again. Batching is a one-off. And the other thing is, yes, it gives you, it provides more information in that sense, less general. At the same time, mint allows you to restrict the rights the new capability conveys. So if you mint a new capability from a capability that has full read-write access, you can, for example, strip the write-write and have a read-only capability that way. So this is one way of capability derivation, minting. Another way is granting capabilities. This is handing a capability, or rather than handing a capability to a new entity as a side effect of IPC. So you can have a transfer of capabilities as an argument in one of these protected procedure calls. And that doesn't copy the capability, it transfers. So the sender loses the capability and it gets handed to the receiver. No, it's actually not true. It's, it just gives you a copy, sorry. I misspoke. In order to be able to grant capabilities over an endpoint, you need more than the just normal invocation rights on the endpoint. You need what's called the grant right. So this is, grant is meant to restrict the propagation of capabilities. And that's important for reasoning about security in a system, in particular about the propagation of access right. So granting is an important way of propagating access rights to someone else, right? If you have a capability to a certain object and you have a way to, you have a grant right on an access point, on an endpoint, then you can send this capability to someone else. By not giving you grant rights, we restrict that. And this is the normal setup. In most cases, clients will have call rights or grant return, or grant reply, as it's called, on an endpoint, but not the grant rights, so they can't send capabilities. And the receiver must have, if the receiver doesn't have a write permission on the endpoint, then any write permissions on the granted capability get stripped off. So that's again a way of controlling access right propagation in the system. You can think of, you have some sort of a data sink, like executing some untrusted program on confidential data, for example. Maybe you downloaded some function on the net which is supposed to do a useful computation, but you don't quite trust it because you think it might leak your private data. In this case, you would try to confine that, untrusted app by giving it an address space which has no write capabilities whatsoever except the right to return a result to you. In that sense, then that process is confined to not leak its data. And you can, for example, then hand it some other capability, for example, to a shared buffer. Well, that wouldn't help in this case because a shared buffer needs write permission. Well, no, you could have a shared buffer, for example, where it's that is used to hand data to this confined confined entity, and by giving it not write access to the endpoint, you can ensure that it will never get write access to a buffer that's passed in via RPC. Okay, so that's one of the use cases for that. And then there's retyping, which is also a way to create new capabilities. And that's the fundament of memory management. And I'll get to that later on. So this is basically the only operation you can do on untyped memory. Remember, untyped memory was memory that is left over, that is not used to anything particular yet. And retype is how you can put it to any specific use. So let's have a look at this capability derivation, a mint operation. So you have a C space, and the C space is a data structure made up of C nodes. So typically it's a hierarchical data structure where a C node is an array of slots. Each of these slots can hold a capability, and some of these capabilities can be capabilities to other C nodes, and that's how you build a tree like that. And for example, the mint will create a capability, a derived capability from something you have access to, so it needs to be in a C space you have access to, and creates a new capability, and you have to provide the slot in a C space where it goes into. Remember, capabilities are pure kernel objects. You don't really get to access them ever directly. So they only live in the C spaces, and so you need to provide a pointer to a C space slot. And this is what this mint operation here shows. So it has a capability which refers to the C space, a destination pointer where the new capability is going to, and the source pointer. These are so-called capability indexes, so they're basically references inside the C space, addresses inside the C space. And then the writes, which is the new writes of this new capability, which is an AND of the existing writes plus whatever you supply here, and a batch if anything. And then if you perform this operation, the new cap gets created in the destination slots, provided all the rights check out, etc. And that destination slot, that's the important point, can either lie in the same C space or in a different one. No, actually it can only lie in the same C space because you only have one C space cap. So at this stage it's only in the same C space, but then the idea is you would then transfer it to a possibly other C space. So I think this is wrong. I need to check. There's a missing argument here. I don't think this can be right. Sorry about that. There's always the same thing, right? You always go through your slides in detail, and then once you teach about them, then suddenly, oh no, this is not correct. So this is probably wrong, and I need to check up on that. Okay, that's basically the operations you can do on capabilities other than invocation. And then is the actual system calls. And earlier I said 2 days ago has about 3 system calls. It's basically read, write, and yield. It's not quite true. It actually has 11, but some of them are basically related and are combinations of the core ones. So one of the 3 is yield, which just drops the rest of the time slice and invokes the scheduler. This is the only capability the only system call that's not authorized by capability, which to me is something that's not quite right with the present model of seL4. But we haven't quite worked out the proper model for doing this, and it hasn't been particularly urgent. That's why it hasn't happened. But I really like to get rid of this for reasons I will talk about later when we look at virtualization, for example. For now, just take it in. It's a derivation of the true religion of having every operation authorized by a capability. And the others are send and receive and combinations of them. And that's why I said there's approximately 3, because you basically have send, receive, and yield. But send and receive come in their different guises and combinations. And the combinations are call and reply receive, which you've already seen, right? Call is the standard operation for invoking a protected procedure call, and reply receive is the equivalent inside the server. And then there's send and non-blocking send. So send basically sends a message to an endpoint, which then the receiver can receive. Whereas the non-blocking version of that one will only succeed if there's a receiver already waiting on that endpoint. Otherwise, it just drops a message on the floor. So send will block the caller until the receiver is ready to receive, whereas MB send will just drop the message if there's no receiver, so it will never block. Similar with receive, you have receive, non-blocking receive, and a non-blocking send receive. And then you have wait and MB wait and MB send wait. And you don't really need to worry about that, because the ones, with very few exceptions, the ones you should be using is call, reply, receive, and sometimes you need a plain receive. And call is, as I explained yesterday, a send phase, setting up a reply object which has been provided by the receiver, and then the waiting for the reply. And because of this manipulation of the reply object, you cannot actually simulate call by send and receive operations. So it has a different semantics from having send followed by receive. The one difference is that it's atomic, whereas a send followed by receive would not be. And I explained why that is not a good thing yesterday. But the other thing is it sets up the reply object, which allows the receiver then to reply back using reply receive. And then there is the reply receive on the sender side, which is also an atomic combination of non-blocking send and receive. And that's a normal server operation. The reason this one is non-blocking is a bit more complex. It's not really going to affect you in a well-designed system. But there are some reasons why this is a good thing. Now, why is the reply receive a non-blocking send versus a blocking send? That was a question. Yep.
Because the call is already waiting.
The normal situation is that, yes, you're replying to a call operation, so there is a client waiting, blocked on the reply. So if there is not, then something is wrong, right? It's a protocol violation. And the only thing that could be wrong actually is that the client got killed in the meantime. It doesn't exist any longer. But that should not be the server's problem. And therefore it makes sense that the server just relies on the receiver being there, otherwise the message is delivered to def 0. And that simplifies the whole protocol. Otherwise there would be a lot of complexity because the server would have to recover from that and all that stuff. So it's much cleaner this way. Okay. So this is in principle all the system calls there are. Which ones apply depend on the actual object type, the type of capability you invoke. So if you have, if you're invoking an endpoint that supports the full set of 10 system calls, but as I said, you should basically only use call and reply receive and occasionally a pure receive. If you use anything else, then you should be rethinking your design. Reply objects, which remember are the things the server provides to the kernel, so the kernel can set up a reply channel to the client, so we don't need an extra endpoint. They are otherwise like endpoints, and they only support the non-blocking send or send receive, which is basically what the server does. And again, I'm not sure whether this is quite, this should not be, this should be a reply wait. There's more wrong with my slides than I thought, and I used them before. And the screen came back. And then notifications and all the other system call object types only support a subset of these system calls. So in notifications, they only support non-blocking send, wait, and non-blocking wait. And the non-blocking send is aliased as signal, which is sort of the logical operation you do on semaphores, whereas the non-blocking wait is the poll operation. Why do notifications not support blocking sends? Remember, there are semaphores, right? You don't block on sending a semaphore. You signal semaphore, and that's a non-blocking operation, right? It just sets it. So there's no, doesn't make sense, right, to have a non-block, to have a blocking send here. Whereas for the wait, it can be blocking or non-blocking, and the difference is the blocking wait is the normal semaphore wait operation you are used to, and the non-blocking is the poll kind where you just look at is there anything there without doing anything to the semaphore state. The wait, if it once it returns, will reset the data word in the semaphore to 0, so it's ready to, it's in the non-sequenced state again, whereas the poll basically just returns what's there without affecting the state of the notification. Okay? And then there is any of the other objects, and they just support calls. And what this really means is any of the other object types, you have to think of sort of being basically invoking a server function that's inside the kernel. So whether it's a thread control block or an address space or a C space, they're basically just server invocations, invocation of privileged code that happens to be running inside the kernel. And so therefore it makes sense to have to represent those as the protected procedure calls using only call. So you can't do a send only on any of these others. And each of them has a type specific protocol. So the kernel for each of these object types defines a protocol basically saying what parameters can you send and what operations that will result in, and what other data you need to provide, etc. So this is basically anything that's in other systems, a separate system call using its own types of parameters, etc., is here abstracted in just calling a capability and thereby invoking the code inside the kernel. The good thing for you is most of this is hidden in syscall wrappers. So the libseL4 syscall interface looks very much more like a normal operating system interface. But they are, if you look at the implementation of those wrappers, they're just small wrappers around capability invocation, and in the end they do a call. So that means you don't have to worry too much about details, you don't have to worry about the fine points of the invocation protocol, because that's basically given by the signature of these system call functions. Cool. Any questions up to here? Yep.
Is it C space per process, or do we just have one C space for the kernel?
Oh, back on that question, it will be answered later, and if I don't, then re-ask. Any others? Yeah, good. So that now gets us into details of the various object types, and in particular the important topic of memory management. So seL4 is quite different from other operating systems you're aware of in many ways, and one of them is definitely memory management. It's pretty extreme in the sense in that it shifts everything out to user land. So basically, kernel doesn't want to have to deal with any memory management, it's all your problem. It's a bit of an extreme viewpoint, if you like, and sort of in terms of the operating system design and design principles, this is probably the greatest innovation in seL4, even though it increases pain level on users, so for you in particular. But it's extremely powerful in point of reasoning about security and safety properties in seL4-based systems. And that's why it's chosen. So for memory management, you basically have three kinds of objects. You have untyped memory, which is the starting point, so that's memory that's not yet used for anything. You have frames, which are representation of physical memory. So untyped, of course, also represents physical memory, but it's physical memory that's not being put any use. You can't do anything else than retyping. Whereas frames are actual physical memory which is to be used by users, and basically the main operation you can do on frames is mapping them into an address space. And the rest are then just these objects that refer to the basic abstractions like threads and address spaces, etc., and have their type-specific protocols. My computer's really playing up. And so, as I said, seL4 takes a pretty radical approach to memory management. And this is sort of captured in this sentence here. The kernel allocates memory when it boots up. It has to, because it has to build up its own data structure. After that, it never allocates any memory. So any memory the kernel needs for any of its operation, you need to explicitly provide to it. And that's the point of all these other object types, which you can retype into. So it's important to understand how this works. So, oops, as I said in this warning here, this is a pretty big foot gun. And it's so big that we didn't really dare to let you loose on naked seL4, and we provide you some libraries to abstract some of that, because otherwise, until you've actually built a system on seL4, it's almost impossible to get this kind of stuff right. So we give you a somewhat higher abstraction level that hides some of this behind libraries. But it's a good point to actually look at what's happening in those libraries to help you understand how the kernel operates. So here are some examples of these C-space operations, and it's a real pain that the screen near me doesn't work. So you have basically, these are the operations that are supported on C-spaces, and so there's operations for building up this structure, this hierarchy of C nodes, and operations for allocating and getting rid of slots in there, and then the actual capability manipulation operations, copy and delete and move capabilities, etc. There's not much point going through these in details. You'll pick them up as you need them, and then look up in the manual what it actually does. Right now, initially, you don't have to deal with those, and if I went through it in detail now, you would have forgotten by the time you need it, so it would be pretty pointless. I'll just list them here for completeness. Okay, so that was C spaces, and then let's look at how actual memory management works. So C spaces are all about access rights. So that a C space defines a protection domain because it's a collection of capability, right? And in contrast, address spaces, they represent the virtual memory space of processes. So they are about actual memory management. And so in seL4, these two concepts are strictly separated, which is quite unlike a Unix system like Linux or something, where your protection domains and your address spaces, they're sort of intermingled. Your address space basically defines what you have access to, plus your group IDs and all that stuff. In seL4, there's clearly separated concepts. The one is the C space that represents capabilities, and the other is the V space that represents a virtual address space. Both basically implement the mapping. What mapping does the address space implement, the virtual address space?
Memory to frames?
Yeah, virtual memory to physical memory, right? The virtual address space is a virtual to physical mapping operations. And your page tables are exactly that, right? They are mapping data structures from virtual addresses to physical addresses. And the C space is the equivalent for access right. It maps object IDs to access rights. And it has a similar structure, and so in that sense, there's some similarities between them, but there's different spaces they map, right? But in the end, they're both mappings. Okay, so how does the memory management work? So, as I said, when seL4 boots up, it just grabs as much memory as it needs to instantiate itself, and then it never does memory management again. What it does instead, it hands all the rights to all the free memory to the first user level process as untypes. So there's a startup protocol that says where the kernel finds the first process, which we generally call the init task or the global resource manager, and it basically sets up that one's text and data segments and hands all the free memory as untypes to that process, and then it gets it started, and from then on the kernel is purely reactive. It just operates on behalf of user of system calls, capability invocations. And then this global resource manager is in complete control of the system. So it's as trusted as anything, but it runs at user level. But because it has all the capabilities in the system, it can do what it wants. And one thing it can do is partition the system. So for example, it can use some of its untyped memory to set up a secondary resource manager and hand that one capabilities to either objects or untyped or both. And then that secondary thing, if it has untyped memory, it can use that completely autonomously. So whenever you have untyped memory, you can create arbitrary objects. You can create thread control blocks or page tables or C spaces or whatever. And because they're all invocation of capabilities, when you have the capabilities, you don't have to ask anyone else. You can just do it. And so by delegating some of these resources in terms of untypes to a secondary process, that secondary process is then completely in control of the subset of system resources. And if you set up a second one with a different subset, and those two subsets don't overlap, then you have two subsystems that are autonomous but completely isolated. And they don't really see anything of the existence of each other except through time. Obviously, the system needs to schedule things, and so by just seeing how much time you get, you can see there's other things happening in the system, but that's about the only thing you can find out about other partitions. In general, that's not what you want, right? Setting up completely isolated subsystems is not normally what you want. You have subsystems on a system for some reason, and typically that means they have to be able to communicate in some way. But they can only do that if that's explicitly authorized by the kernel. And how does, or by this global resource manager. And how does that resource manager authorize the two partitions to communicate? What does it need to give them?
Capabilities?
Like what? For communication, you want endpoints, right? Or maybe notifications or something, or shared memory, or both, right? So that's how you then can basically create controlled communication channels between those subsystems. If they're not there, no communication possible. And so this is really the core of being able to reason about security and safety in seL4 based systems, that we have this bulletproof isolation where we can reason about to the degree that we can prove independence, etc., and security. And this can be done hierarchically, and it can be revoked, etc. It's all a question of what access rights you have, what capabilities. And the basic mechanism that enables all that is the retype. So retype is putting unused memory to use. It's the only operation you can do on untyped memory, and it makes the memory typed. So if you have a slab of untyped memory, that's the UT down there, the black thing, and that's represented by the capability on top, then I can invoke a retype operation on that capability that says, okay, I want retype into, in this case, 2 to the 2 frames. So I want to retype the first bit of this large untyped slab into 4 frames. And the system will do that and return 4 frame capabilities to the caller. And now you have capabilities with full access rights to each of these frames. So in particular, they have read and write rights, and that can be invoked. And then you can do more retype something into C nodes, so you have capability storage, and retype something into thread control blocks, so you now have threads, and so on. And if you have a read-write cap, you can mean the read-only cap, etc., and you can revoke that, and all that. So basically, retype is the basis of making memory useful. And you can see this is how providing memory to the kernel works. As I said earlier, the kernel doesn't do memory management. If you try to do any operation that requires the kernel to consume memory, then you do that by retyping. So retyping untyped into thread control blocks basically means kernel, give me threads, and here is the memory to allocate these thread control blocks to manage those threads. So it's basically giving the kernel storage for metadata. And importantly, because as long as you hold the capability to this memory, to these kernel objects, you can obviously revoke them. So if I created these threads and I keep the capability to the thread control block, I can simply revoke that, convert it back into untyped, and of course that means the thread goes away because it's no longer represented in the kernel. So that's the way to completely destroy a thread, for example. Okay, and now to make all that useful, we need obviously address spaces. So address spaces, as I said, are mappings from virtual to physical addresses, and they're represented by page tables. And the seL4 page table address space abstraction is really a very thin layer over around hardware page tables. And that in particular means that the address space abstraction looks different between different architectures, because it doesn't try to provide a hardware abstraction. It just gives you really the minimum you need to safely manipulate page tables. So the two main architectures, ARM and x86, are pretty similar in the sense that they have these hierarchical page tables. On 32-bit ARM and x86, it's 2 levels, and on 64-bit, it's four levels in the ARM case and 5 levels in the Intel case. And they are pretty much like page tables. You have, in the 32-bit case, you have a page directory, and the page directory points to page tables, and the page tables contain mappings to frames. Except here, of course, everything is done by capabilities. So your seL4 page tables, they don't contain physical addresses, they contain capabilities to frames. Makes sense, right? And so how do you build these up? You have a page table, 2 page tables here. One is mapped into a page directory, the other is not. So as long as it's not mapped into a page directory, you can't really do much with it. If you want to actually activate it, you need to map it in a page directory, and this is done by this page table map operation, which inserts the capability in the page directory, and then that makes this page table part of the address space. Of course, at the moment it's still unpopulated. It doesn't contain any caps to frames, so any address in that range would still not resolve, but the other page table does have caps to frames. And then if you have a frame table, a frame capability, then you can insert that into the page table as well. And then that part of virtual memory actually becomes defined. It's now mapped to the frame. So pretty much what you learn to do with frame tables, except rather than physical addresses, we use capabilities. And importantly, the top level page table, which depend on the architecture, has different names. In the ARM 64 world, it's called the page global directory. This is the address space as far as the kernel is concerned. So you have rights to an address space if you have a capability to a page global directory. That's the representative of the address space. And if you delete that one, then you blow away the virtual address space. Any questions? Oh. And these are the operations here. And I probably should walk up to it. You can see that we do an alloc, so that creates some untyped, a bit of untyped from a larger area, and then retypes that into a frame capability, and then there is a that frame is then mapped into the page table using a mapping operation, and the page table is referred to by its global directory capability. I really we think we made a mistake there in how this API was chosen. So the mapping a frame into address space is an invocation of a frame capability using an address space as a parameter. It should actually be the other way around. It should be an address space invocation that takes the frame as a parameter. One of the side effects is you can only do one mapping at a time. If it was a C space, a V space in operation, then you could have several frames as arguments to insert at the same time. So there's some efficiency penalties. It's been not painful enough yet to change it. That's a drawback of having a verified kernel. If you change anything, you have to change the proofs, and that's typically much more expensive than changing the code. So there's a great reluctance to change anything. So in a hardware page table, as you know them, they contain virtual addresses, physical addresses, and access rights and caching rights typically. And this is completely similar, right? It contains the same things, except instead of addresses, it's actually capabilities. But they map directly onto hardware page tables. And but the important thing is you completely need to keep track of this, because that's the operating system's job, right? If you set up mappings, you need to make sure you keep all the information, etc., in order to do that, to undo, etc. So this is a significant amount, a source of complexity. And when you have mappings, you can undo them by doing unmap. And there's again the functions here. seL4 arch page unmap. Arch refers to an architecture specific API. You can unmap a frame, and then you can delete the entries in the C space, etc., free up the slots, and recycle the capabilities. So this gives you basically undoes the retype, and you get the plain untype back. And again, this is a poor API choice, because the unmap again operates on a frame. I think it should operate on a virtual address, but it's not going to change in a hurry. And then there is shared memory, which is really important. In most cases, you need access to shared memory. Now, what I can try is, maybe it works better if I have VGA.
It's set up for VGA right now. It's VGA.
Doesn't look better, huh?
Maybe give it a bit of sec. Just give it a second.
Today is not our lucky day.
All right.
Okay, we're back. It's a bit
Blurry.
fuzzy, but better than nothing. Let's not change anything. So shared memory means that you have multiple virtual address space mappings, multiple virtual pages mapping to the same physical frame, right? And that's how you can share memory either inside an address space or between address spaces. And in seL4, one thing you need to understand is a frame capability can only be mapped once. So if you want to share a frame between different virtual address mappings, then you need to have different capabilities to the same frame in order to do that. And that's an implementation restriction, basically because there's not enough bits in the frame capability to set up the book counting we would need for keeping track of the sharing. So it's again the usual thing: if there's a problem, make it the user's problem. The kernel doesn't care, and it makes the system a bit harder to use, but that's not the whole point, right? Good kernel design is not a usability issue, it's what you can do with the kernel. So if we want to do a shared frame, then we need to create a new frame capability. by copying an existing frame capability, and then we can map that one into the second address space. So we duplicate the capability and then mapping. And that's how you set up shared memory. And I already said that. And then there's various ways, operations you can do on that. Basically all the usual stuff as before. Okay, any questions up to this point?
Are the frame capabilities, are they stored, they're stored on the frame that they refer to, right?
They are the which capabilities?
So the frame capabilities are...
They're stored in the C space like any cap. Right? You have your the frame gets created. The frame is an abstraction. It's a kernel abstraction for physical memory that can be mapped into virtual address spaces. So you create a frame object. You don't create frames, right? They're there. But you create a frame object by retyping some untyped object into a frame type, which just means that that physical frame, before it was not usable for anything other than untyping, now you have a reference that allows the right to map it into an address space. And that capability that you just created, it's only a bookkeeping thing, if you like. You create a capability to that frame before you didn't have one. And that capability lives in your C space. And then you can map that into a virtual address space by saying, okay, here's a capability in address space and the right places for putting it all in, and then you establish a mapping.
Right.
So nothing happens to the frame itself, but your rights on the frames change.
Right. And that object will have a reference to the frame. What I might be a bit shaky on is, we're putting it into the page, if we put the capability into a page table, how does the hardware map to the frame?
We're not putting the capability in the page table. We're putting the capability into a vSpace object. And that results in the kernel inserting the data into a capability. So you basically, but it's a very good question you had, and I didn't properly explain that well enough. So in the end, of course, the kernel maintains page tables because that's what the hardware sees. But it presents to you this abstraction of these slots of capabilities. And that's how you manipulate them. Again, you can't directly access the capabilities. You can't directly access the page table objects either. You can only tell the kernel, put this capability in that slot. And of course, that means the kernel really puts a physical address into a page table.
Okay, makes sense.
Good. Any other questions?
What's stopping you from retyping runtime memory multiple times?
The kernel does. That's part of the basic integrity conditions of the kernel, that there cannot be overlapping mappings of untyped memory. Also good question, yeah. Any others? It's 5 to the hour, perfect time for a break before we move on to threads. Are we ready? Okay, cool. So let's look at threads next. They're relatively easy compared to memory management. So as fairly typical, you have a data structure called the thread control block that represents threads. And most of the stuff in there, it should be pretty familiar. That's pretty standard. So you obviously in a thread, you have a reference to its address space. So that's the vSpace in seL4. Obviously, seL4 specific, you also have a reference to a C space that contains your capabilities, therefore defines access rights. Then there is things that are needed for exception handling. So every thread has a fault endpoint and optionally a timeout endpoint. And I won't talk about timeout endpoints today, but later when we have to talk about real-time issues. So the V space, as I said, is represented by the capability to the page global directory, the C space by a C node reference, which represents the top level of the C space data structure, fault endpoints for exception handling. Then there's the IPC buffer. I mentioned already on Tuesday that IPC data is transferred in virtual registers. Some of them map to physical registers and the rest map onto this IPC buffer. And then obviously you have an instruction pointer and a stack pointer and general purpose registers, so the usual thread context that gets context switched by the kernel. And then there's some scheduling data, and there's basically 3 bits of scheduling data. A priority, which is pretty standard, the maximum control priority, which you can ignore for the time being. That basically limits the way to which a thread can manipulate its own priority. And then the scheduling context, which is the right to access the CPU, and I'll cover that later. All of this needs to be explicitly managed, goes without saying. We already looked at how the V space and the C spaces get managed. And part of the normal setup of a thread is to set the stack pointer and instruction pointer. There's nothing specific to it except how the specific APIs here. And then it's a set scheduling pointer, as we do later. So to create a thread, you create a TCP object. And that, as far as the kernel is concerned, that's the thread. It's not schedulable or runnable. You need to provide a few more things to make it there. And this is done by configure, which allows you to set these thread attributes. In particular, give it a V space and a C space. Without those, it can't do anything. And the scheduling parameters. And the write register call is used to change the values of the user visible registers. So in particular, the stack pointer and the instruction pointer, which of course the thread needs to run. And after that, the thread can run, provided it's got time. And these are the APIs you use for that. So there's a trivial example of a thread function up there, which just has an endless loop. And in order to create that, we map a frame for the IPC buffer. We allocate a slot in the C space, and then that gets retyped. Some untyped gets retyped in a TCP objects, and then we use the configure operation to give it these attributes it needs, including a V space and a C space and the exception handlers. And then there is another one to set up the scheduling parameters, and that's what it needed. So it's basically boilerplate, and we recommend that you put that into a library. The reason that is not already there because that implies policy, right? How you allocate your stacks, etc. That's a operating system policy which you need to implement. So this is, even though that's not particular seL4 specific, this is sort of the low level management which you need to be in control of, and which is easy to stuff up, and you can produce the bugs that are hard to find. So in particular, your stacks, you're in complete control of the stacks of any thread. The kernel doesn't give it a thread. The kernel only has a thread control block, which basically contains all the context and stuff, and the rest is your job. So you need to find memory to allocate a stack in, map it to the thread, define the stack pointer, etc. That's all your job. And one of the things that a lot of people run into is stack overflows, which can be really hard to debug. So the typical case to produce those is big automatic arrays. So assume you have, for example, 2 threads in this address space. Each one has to be given a stack at non-overlapping locations, obviously. And obviously you want to keep them far enough apart so they don't run into each other, otherwise you get funny results. But that's not enough, because one of these things could just allocate a big array. So this is a typical way to shoot yourself in the foot. You have a big automatic array, in this case 10 kilobytes, which is largely bigger than your stack. And so if that gets allocated on the stack will overflow and override any data that happens to live in this address space above the top of stack. And if you do that, you get very strange results and scratch your head for quite a while. And if that happens, look whether you overrun your end of stack. So my recommendation is always leave at least one unmapped page on top of the top of stack to reduce the risk there that you get into some really weird things. You get effect like, oh, memory is changing. Before it had this value, now it's got that value. I didn't touch it. Well, you probably didn't done something like that. So by having above the top of stack at least one frame unmapped, that means you get an exception when you try to access it, so that helps debugging. So this is some boilerplate on how to create a thread in a new address space. So this is when you set up a new user process. Then you need to do a few extra things. So the standard stuff you did before is create frames for the IPC buffer, allocate a stack, allocate a TCP, etc. And then you need to create a new global page directory object for the new address space, and give it a new cap for the syscall endpoint. So somehow this new thread needs to be able to invoke the operating system, right? It has to have an endpoint for invoking the operating system to do system calls. So the system calls, of course, for any of your threads is just invoking your OS through an endpoint, calling the endpoint. So that needs to be done. And then this needs to be all put together. So we have create a new C space by allocating, by retyping some untyped. And then we need to set up the new executable. Presumably this new thread has a new kernel, a new image. So copy that from your image that contains all the preloaded data. Set up a stack, copy the executable text into the text segment, and then do the configure IPC, specifying the instruction pointer, which you extracted from the ELF file in the end. So this is assuming you already processed to the point of doing ELF loading. Initially, it may be a bit different. The ELF file itself has headers which contain, among others, the starting address of the program. And this is what you need to set up the instruction pointer with. And of course, the stack pointer is what you determine. And then you set up registers to define the stack pointer and the instruction pointer. And the rest is like a normal thread. Questions?
Do you recommend we familiarize ourselves with the ELF format, or should we just leave it to live?
The project spec will tell you what to do, basically. But eventually you get to the point where you can load a normally compiled ELF file. Any others? Cool. So that's threads, and related to threads, of course, is scheduling, and the abstraction for scheduling is the scheduling context. So I already told you that there's basically three parameters you have for scheduling. The one is the priority, the second one is the MCP, which you can ignore for now, and the third is the scheduling context, which is a capability that represents the right to use the CPU. And without a scheduling context, you don't have the right to use the CPU. That means the thread is not runnable. Among the runnable threads, seL4 is a strict round-robin, a strict priority-based scheduler with round-robin within the priorities. And the kernel will always, at any time, run the thread, or if there's multiple, one of the threads with highest priority among all the runnable threads. So in particular, unlike sort of the fair share scheduler in Linux or any of these things, the kernel will never manipulate the priority of a thread on its own. This is thread priorities only change if requested explicitly by a system call. In that sense, the kernel doesn't have a notion of fairness in scheduling, and that's intentional because we want to be able to make guarantees of what happens in the system. In particular, we want to be able to guarantee real-time behavior, and therefore we have to strict priorities. If you want to change things, then you can implement that on top by manipulating kernel priorities. So if your thread has no thread control, no scheduling context, then it doesn't have the right to access the CPU. It's not runnable. It's not in the run queue. The scheduling context contains basically two parameters, a budget and a period. And the budget gets consumed when the thread executes. And if the budget is completely consumed, then again the thread ceases to be runnable and it gets taken out of the run queue. How does it ever get runnable again? This is specified by the period. Once the period is up, then the thread will get a new budget and is runnable again and can be scheduled. In general, the budget has to be less than or equal than the period. If it's equal, then you just basically get a simple time slice, and multiple threads with the same priority that have a what's called a full period when the full budget, when the budget is equal to the period, they just get round-robin scheduled. For your purpose, you don't really you don't have to worry about budgets and periods. You basically, unless there's any specific other need, you create your user processes with just full budgets. So give everyone the same period and the budget that's equal to the period, and that then is just a traditional time slice. And the thread will execute until the time slice, which is the budget, is depleted, and then it gets put at the end of the scheduling queue at that priority. If it's the only one at that priority, it will immediately get scheduled again. Otherwise, someone else gets a go in round-robin fashion. So that bit is pretty straightforward. So as I said, aim is real-time performance, and not you can implement arbitrary schedulers on top. Any questions about scheduling? Yeah.
Who sets the budget and the period?
You, like the operating system.
So what's stopping like every process from setting like a really big budget and period so the system just
Well, this is the policy you define in your operating system, what kind of budgets you hand out. That's why I said, for your purposes, just give everyone, say, millisecond or 10 millisecond period, and the time slice that's the same as the period, and then you just get traditional time slicing. Any other? Yeah?
Like following on from that question, for priorities, wouldn't a user program be able to set a certain priority, like to the highest level, or is there any choice?
So for your project, it's okay to give all the user processes the same priority. I don't think there's any need of assigning different priorities, but you definitely want to keep them lower than your operating system. And that's in line with what I said 2 days ago, that a protected procedure call should always go to a higher priority. It makes sense, right? Your OS runs the higher priority, and the clients just invoke it. More questions? No. Then final topic is interrupts and exceptions. So obviously there is abstractions around those. They're sort of similar yet different. What's the core difference between an interrupt and an exception?
An interrupt can be externally generated. An exception is within the kernel or within the program.
Yep. So in particular, an exception is triggered by a particular action of your program that's executing. And in that sense, it's strictly synchronous with execution, right? An exception is triggered by a particular piece of code by a particular action it's doing at that, and it occurs at that time. There's some ways in which this is weakened in modern architectures because exceptions can be imprecise. That means they can come in later, but that's an order of a dozen cycles or something like that. But in principle, they're strictly synchronous events, synchronous with whatever in the execution triggers it. Whereas interrupts, of course, are strictly asynchronous, right? They come in from a physical device that's in generally not synchronized with execution, so they can happen at arbitrary times. And that means they are represented by different kinds of abstractions in seL4. Interrupts being synchronous map nicely onto endpoints. Because when you trigger just after that, exceptions being synchronous map on endpoints. Because when you trigger an exception, this is not different from invoking a server function, right? And as a matter of fact, at the hardware level, that's typically the case. Like there's a syscall instruction, which basically is an exception that invokes an exception handler. So that's basically means exceptions naturally map onto endpoints or predicted procedure calls, whereas interrupts, they're being completely asynchronous, they map naturally onto notifications. And that's how it's implemented in seL4. So for exception handling, first there's different exception types, and most of them are basically modeled the same way. You have the nice thing about being verified, you always know what they are because that, it's well defined what kind of exceptions exist. So there's an invalid syscall, which basically means there's a syscall instruction with an invalid argument, and that can be useful for instruction emulation in days where many microprocessors didn't have FPUs. This is a typical way of doing floating point emulation. You just use a floating point instruction even though your process doesn't have an FPU. So it triggers an exception, software gets invoked, implements the floating point instruction and returns. Virtualization can use that. Capability faults, this is where you either refer to capability that doesn't exist or is invalid in the C space, so the C slot is empty or invalid. A page fault is pretty obvious. You reference a invalid address or which could be an unaligned access, or it could be an address that's actually not accessible by users. So depending on architectures, some architectures reserve the top half of the virtual address space for privileged mode. And so if you try to access one of these, you get an invalid address. Obviously, if you try to access an address that's not mapped, so there is no entry in the respective page table, then you get a page fault. And this can be a fault in the program, or it can be something that's just normal. For example, the stack needs to grow, the heap needs to grow. To the operating system, they represent themselves as page faults, and then the operating system needs to distinguish what kind of page fault it is, what do I have to do? Do I have to grow the stack? Do I have to grow the heap? Or, depending on how you start a process can either be started completely empty, and of course, the first thing it does is it tries to fetch from the instruction point address. There's nothing mapped there, in which case that will trigger page fault. Your operating system needs to resolve the page fault by realizing, okay, where does this map to? Oh, it maps into a text segment address. I better copy that part of the text segment in there and establish the mapping. The next thing, then it would touch its stack, and the same thing happens. Stack is unmapped. Okay, it's actually a valid stack address. I allocate a frame and map it into the address space and then continue. Or it can be something, just some fault, the address access, in which case you kill the process or the tree. And then there's architecture-defined exceptions, things like divide by zero or unaligned accesses. For your purposes, you can just kill the user process that's trying to do that. And all these map into invocations of the fault endpoint. So your thread executes, it triggers these exceptions, and that's literally gets simulated by the kernel as a call on the fault handler. So your fault handler is a server that listens to this endpoint, and when the exception happens, the kernel fakes basically a call. It pretends that your thread did a call operation on this endpoint, and that invokes the fault handler, which is really part of your operating system, right? This is how, for example, syscalls happen, or whether you want to treat them as the same as syscalls or separate handler, etc., that's up to you. Basically, your fault handler needs to determine, is this something that should be handled, or is it an illegal operation the thread is trying to attempt, and we just shut it down. And all the exceptions map on this this invocation of the fault endpoint, except for the timeout, which has its own exception handler, and that's an optional one. So a thread doesn't have to have a timeout handler. If it has one, then this gets invoked when it runs out of budget. In your case, it's something you don't want to worry about, so you just don't give it a timeout handler, and then whenever it runs out of budget, it has to wait till the budget gets replenished and can keep operating again. That's all I got to say about exception handling. Any questions? Yep.
Does every thread have a capability to the fault endpoint then? Like
Yes.
created?
Yes, that's part of what if you look at the code back, which the boilerplate for setting up a thread, it has to have a fault endpoint. It doesn't have to have a timeout fault endpoint, but the normal fault endpoint it has to have.
And that EP, is that kernel provided, or does the program provide that for itself?
The what?
The EP. So I guess the EP.
Oh,
and the
this is what your operating system does, right?
Okay.
So in terms of the kernel, yes, it's the user. In terms of your project, you do it. And typically, a typical design would have the same fault endpoint for all the user level threads you create. Same as you have a single syscall endpoint, and they may or may not be the same. Any other questions? Okay. Interrupts. As I said, while exceptions naturally map onto endpoints, interrupts naturally map onto notifications. And they have two special hardware-specific, or one of them hardware-specific objects. The one is the interrupt control object, which is, that's, if you like, a virtual object, doesn't really exist. It's sort of you can consider it as an abstraction of the interrupt controller. But really, all it is therefore to control the right of associating interrupts with interrupt handlers. So if you have a capability to the IRQ control object, then that gives you the right to establish interrupt handlers for particular interrupts. And that's all it does. And then you have, for each interrupt source, you can have a separate IRQ handler, and there's a protocol for establishing those that requires access to the IRQ control object. So if you have the IRQ control object, then you can create interrupt handlers by associating a function or a server with an interrupt source. And in particular, bind a notification that represents the interrupt. So the way the kernel abstracts the interrupt is, if an interrupt has a handler associated it, and then it can have a notification, and that means the kernel will signal that notification when the interrupt happens. So here we have our IRQ handler, which is being created by the means of having access to the IRQ control cap. and that's associated with a notification. And the operation to do that is set notification for associating the interrupt. And then you can wait on that, and this is basically what an interrupt handler does. It waits on the notification, which means when the notification is signaled, that means that the interrupt has been raised. And then it can acknowledge that one. And is the boilerplate for it. So you have cat IRQ control is the capability to the IRQ control object capability. Once you have that, you can invoke this IRQ control get API to associate this interrupt with a handler, and then you can associate that one with a notification, and then you can wait on that notification, and you use the IRQ handler acknowledgement function for acknowledging the interrupt. Important thing is when an interrupt happens, serving that basically requires 2 send and 1 receive operation, because your low-level interrupt handler waits on the notification. When it happens, what does it have to do? It has to somehow inform the rest of the operating system, right? This data has now come in, deal with it. And then it has to acknowledge the interrupt and go back to waiting for the next interrupt to happen. Unfortunately, we have only a single send and receive combination system call. We don't have a system call that allows to do 2 sends and a receive at the same time. So you need to have 2 explicit system calls here. One is the acknowledgement, and the other one is the tell the rest of the operating system that the data is available and go back to waiting. We haven't run into real performance issues there, but we haven't really done too much in analyzing I/O performance. This is going to happen very soon, thanks to Lucy. She'll have fun, and then we'll find out whether this is an actual bottleneck or so. So far, it hasn't been, because the systems we build on seL4 so far weren't really all that sensitive to the overhead of processing I/O, as long as it was done correctly. So I'm curious to see whether this extra system call actually does turn into a noticeable performance issue or not. Okay, now if you understand how to deal with interrupts, then that's basically what you need to do device drivers. So what's a device driver? It's obviously a user-level process, because it's all there is. Minimality principle, there's no need for device drivers to be in this kernel. And the thought of having USB stacks and audio drivers and all that crap in the kernel is just crazy. But that's what Linux does. So in seL4, a driver needs to deal with the interrupts, inform the rest of the OS, and program the device, which is reading and writing device registers. And the device registers on ARM are all memory mapped. So they're just doing reads and writes from specific location. And how you communicate with the rest of the OS, that's your design issue. As I said, on ARM it's all memory mapped I/O. So in order to find what you have to do is your boot info tells you which frame your devices are mapped in, and you basically need to map that frame into the driver's address space, and then you can access the device registers by reads or writes. Unfortunately, we abstracted a little bit too much for my taste in the present version of the program, so you don't really do much with device drivers. You write a simple one for the timer, but you don't get to see the full complexity here, which is a bit of a shame. But we have to fit it into the time available somehow. And yeah, there's a special system call for device mappings as opposed to other frame mappings. This is mostly an artifact of that you might have to specify particular permissions, which I don't really think is an issue. But it's mostly for dealing with 32-bit architectures that have a larger physical address space than the virtual address space. So if we only had 64-bit architectures, we wouldn't need this distinction. It would be a normal map. Okay, that's all you need to know about device drivers. There's a bit more complexity obviously hidden below that, but it's all you need to get through the project. Any questions on this? No? So that's the end of the seL4 concepts. I've basically now told you everything you need to know and want to know about seL4. I will give you a bit more hints about system design that might be helpful. So one is a reminder of what I said 2 days ago already, that in general, unless your system only has short running or your server only has short running invocations, you can't get away with just multiplexing a single return object. You need to have multiple ones, and I already said that. And this is just reinforcing that. So because your client basically blocks on the reply object, if you have multiple concurrent client requests, then each needs its own reply object, because as soon as you receive, as the server receives from the endpoint, providing that reply object, any previous state in that reply object will be overridden. So if you have, for example, what you will have, you have long-running I/O operations, right? Your clients do I/O, and that means you may have to fetch data from our simulated disk, which is basically a network server, but which has too much latency. You want to block the client and then be ready to receive new client requests. If you're just using a single return object, then by the time you receive the next request, you have lost the state you need to reply back to the original client. So you need to have several reply objects here. So this is important. Questions? No? The other thing is, I sort of alluded to this, and this comes back to a question someone here asked. What's a process in this system? And in terms of seL4, there's actually no concept of a process. seL4 only has the concepts I told you about. It has threads, address space, and C spaces, and etc. And our normal notion of a process, and you will be implementing such a notion in your project, is a combination of those. So a process or task concept incorporates a lot of these basic seL4 concepts. So in that sense, it's a higher level of abstraction, which seL4 does not provide. You implement it in your OS. So a process or task obviously needs a virtual address space. So that's a V space in seL4 speak. It has a protection domain, which in seL4, it needs capabilities to perform any operations. So in seL4, that means it has to have a C space. It definitely has one or more threads, because there's no execution without a thread. It may or may not have a scheduling context. A user process in general needs a scheduling context. So if you create a user process, you need to give it a scheduling context. Why is a scheduling context not necessarily needed for process? Answer is given here. Because a server that's invoked by a call operation gets passed, if it doesn't have its own scheduling context, gets passed the client scheduling context and operates on that one. That's a really nice feature, because you automatically account the server time correctly against the client.
So the server's, you said, not runnable, but then when it's passed the scheduling context, it then is runnable for a moment, and then it's not again.
Exactly, yeah. Obviously, you need some special, somehow you need a scheduling context to get the server set up in the first place. because it can't get to the point where it does receive the weight on the endpoint unless it has been given a scheduling context. So you can do that in various ways, for example, giving it a scheduling context and then revoking it later. Or notifications can also be associated with scheduling context, and if you receive from a notification, then, well, that still you need to be able to receive from a notification. So if you don't have to do this scheduling context-free server, you can have your operating system, and that simplifies life in terms of just getting the thing initialized mostly. So just give your operating system server scheduling context, and then you don't have to worry about that. But in a way, the cleaner way is to have your OS server not have its own scheduling context and operating on behalf of the client. But that complicates design, not only on the initialization part, but also when it has to deal with I/O, etc. So my recommendation would be just give everything its own scheduling context, but I just want to point out that it's not necessary. A process can exist, only really a server process can exist without its own scheduling context. And almost certainly it needs some sort of endpoints because it needs to do something, right? Your client, your user thread needs at least an endpoint to talk to your operating system, so that's the syscall endpoint, and it needs a exception endpoint, which may or may not be the same thing. And again, it's a design issue whether you want to keep them separate or multiplex them into the same thing. So it will definitely need at least that much, and in general you want notifications as well. But that's basically how you build a task out of seL4 abstractions. And this is important. A task may not, or a process or whatever you want to call it, does not necessarily have to have the rights to its own C space and V space, and that's generally a feature, right? You want to keep control of all the system resources and access rights, etc. And you do that by not giving the user task capabilities to its own V space and C space. You keep those in the operating system. But of course, you can have system design where you do allow that, but that would be introducing complexity which you probably don't want to have in your project. Also, the typical design is that every process has not only its own address space, but its own C space as well. And the difference, of course, between a single-threaded and a multi-threaded process is just whether you have one or more threads sharing a V space. The same applies to C space. You can share C spaces between threads across address spaces or not. In general, there's probably no good reason to share C space across V spaces. You probably want to give everything that has its own address space also its own C space. But you can build sort of more arbitrary models by having the two separate. Okay? Questions on this? And then I already mentioned that you will generally need shared memory. And this is almost certainly required just to be able to use a POSIX-like file system API, for example. If you think of a monolithic OS like Linux, then the kernel has access to everything, and all the services are in the kernel. And if a user does a syscall, for example, a read or write from a file, then it just gives the kernel a pointer to a buffer, and the kernel has access to all memory, so it just goes there and resolves the buffer address in the user's address space, and then goes to the physical memory or goes through the virtual memory, whatever, right? You have naturally shared memory between the server, between the client and the operating system. In your case, that's not the case, and you need to set it up explicitly. Because by default, you have your server, which is the operating system, and your application, and in order to do a bulk data operation, like reading or writing from a file, you need to, the client needs to provide a buffer to the operating system to put the data in or read it out. And that in general means they need to share this memory. And you can either set up explicit shared memory between your OS and your applications, or just simulate the monolithic case and mapping all user memory into the OS server address space, which is definitely the simplest way to do it. That's what I would recommend. Okay? Yeah. Any questions on this? Typically, there's other uses of, if you have a really sort of well-structured microkernel-based system, then you would have all drivers in there, each driver in its own address space, your network stack or stacks in their own address spaces, file servers in their own address spaces, and they communicate via shared memory. And you typically do that in form of some ring buffers in shared memory, shared between, in this case, the driver, network driver, and the IP stack, and then notifications for synchronization. You don't need that for your project, but this is the way to give high performance zero copy I/O in a microkernel based system. And then some project specific things. We give you a few libraries for, as I mentioned earlier, for sort of reducing the target surface of your foot. In particular, UT, untype, and some others, a C-space manipulation library, and they basically communicate with each other by either function calls, so you map these into your process, or system calls via seL4. And C-space manipulation is just very messy and complicated and easy to get wrong, so that's why we give you that library. And the UT library for retyping from untyped into actual memory objects is also, we provide you that as a starting point. You will need to extend that for your own needs. So the existing UT library we give you is sort of very rudimentary. You want to build on that. So you need to have a look into that and understand how it operates. It's a good idea to have a look into the C-space library as well, but you probably don't need to touch it. And then a few warnings on memory management. The UT library is a very simple body allocator, and that means just because you free two objects of size n doesn't necessarily mean you can then allocate an object of 2n, because if they may not be contiguous in memory, in which case you don't get that object size. So be a bit careful about this one. You need to understand object sizes. So you can see all the object types are either page size or fractions of a page size. So a frame obviously is a page size. Makes no sense otherwise, same as the page objects. They're all page size granularity. And generally all the objects have to be aligned to their size. Endpoints are 16 bytes long. But obviously you can only retype in page granularity, because in the end that's a manipulation of page tables. So that means when you allocate an endpoint object, you get not just one endpoint, you get 256 endpoints. Similar notifications, they're a bit bigger because they have the extra data word. Scheduling contexts are variable size, but unless you get complicated, they're just 64 bytes. A C slot in a C node is 16 bytes. The C node itself can be bigger than a page, so you can have multi-page C nodes, which is not really necessary in your case. And TCPs are 2K, which is a bit annoyingly big, but these days memory is not so much an issue anymore. So just be aware that you generally don't allocate individual kernel objects. You allocate a page full of these objects, which is what's actually been shown in the example I went through about how untyped retyping works. This question was asked before. What if can you try to retype the same untyped into multiple objects? No, the kernel will not allow you overlapping objects. Once you retyped a bit of untyped, it's in use, and you can't retype it any longer until it gets revoked. But if you try to do something like that, you will have fun debugging, so be careful. Again, the existing library does the work for you, but you will have to build on that. And yeah, even though you sort of operate on a somewhat higher abstraction level due to the libraries we give you, you sort of have to have an idea what's happening underneath, because otherwise you get funny effects you don't understand. Yeah, so this is a very easy beginner's thing. Okay, I've got untyped. I'll convert everything into frames. Well, that's a bad idea, because there's only one thing you can do with frames, is mapping it into an address space. But you need other objects as well, right? You need thread control blocks, and you need C space and all that stuff. So once you set up a frame table initially, make sure you keep enough free memory to actually keep your system operating, and just once you retype something into frames, you can only hand it to users. And this is the platform you're working on, or the high-level architecture design of the Odroid. So it's actually a quad-core chip. It has 4 Cortex A53 64-bit ARM cores on there. And it has a whole bunch of peripherals, of which you get not to see most of them, or don't have to worry about most of them. The things you deal with are the serial controller. There's a driver given there. You have a timer. Obviously, the kernel consumes some timer for itself to be able to provide preemption. And you will write a symbol driver for one of the timers. And then you have an Ethernet, which you don't have to deal with directly. We give you already a driver for the Ethernet to make your life easy. And then there's other stuff, and it's got 2 gigs of memory. Any questions? I'll leave you with an example of seL4 in operation. This is the Boeing unmanned Little Bird, a pretty dated helicopter airframe they converted to autonomous flight. And this is a flight, there's a pilot in there because they need that for FAA certification, but the pilot doesn't actually change the controls, so it flies around autonomously around the Arizona desert, and it's running on seL4. Cool. That's it.